Okay, so in the last segment, we looked at how we constructed a model for Gibbs energy and its variation with composition called the regular solution model. And we came up with this formula that the Gibbs free energy of mixing was composed of an XAXB times a work of mixing plus an entropy term. And if we then need to add on to that the Gibbs energy of the original two buckets we had, the A and the B bucket. Remember, we were combining A and B to get our purple, if you like, alloy. So we've got to add on to that the energy of the original set. So that's a G of A times XA plus G of B times XB plus our delta G mix. So that's our overall Gibbs energy. And what that will look like is a curve that goes from GA over here for pure A, and then it'll look like this delta G mix superposed onto it, so it'll do something like that, say. And this would be the Gibbs energy of pure B. And you've got in between a variation superposed on a straight line here, if you had a straight line going across there, that variation which is coming from this delta G mix. And what that gives rise to is if we consider an alloy here, it can lower its overall energy by forming an alloy that's a combination of these two over here. So if we took some of an alloy of that composition and some of an alloy of that composition, then we'd form an alloy with an overall energy which was here. So what that means is an alloy here can decompose into an A-rich phase and a B-rich phase. So this is a Gibbs energy curve, say, for a phase alpha, and it can decompose into an A-rich alpha 1 and a B-rich alpha 2. And the overall energy you'll get, if you go through and take the lever rule, then the overall energy will actually be that number. Because the lever rule conservation of atoms means that you've got a volume fractions of alpha 1 and alpha 2 that combine such that you could get to an overall alloy composition here of C, whatever that is, some alloy composition. And that means that when you combine the volume fractions, you end up going along this straight line to find the average energy being that overall. And so what this means is that an alloy here will decompose into two components. So what that will look like on a phase diagram, so if we come down here, what that will look like on a phase diagram is it'll look like a phase separation. So if this is our phase diagram of temperature going from pure A to pure B, up at high temperatures we'll all be in a phase alpha. But at lower temperatures, then we'll decompose into an alpha 1 and an alpha 2. And this will then be an alpha 1 plus alpha 2 two-phase region. So up at these high energies here, the Gibbs energy curve would look something a bit like this. So we'd have a Gibbs energy curve where we were up at high temperatures, we were dominated by this entropy term, and that had, a curve that was always a negative. So we'd always have then a curve for our Gibbs energy up at high temperatures that looked probably something like that. And that would be then up at high temperatures. And there would be no minima here. None of these minima occur in this curve. There's only one. So there's no way for an alloy, say at this composition, to decompose itself into two A-rich and B-rich compositions that lower the overall energy. So you can't draw a line here where you take one over here and one over here and lower the overall energy. If you do that, you raise the overall energy. It goes up, so that won't happen. That's unfavourable. You always want to go to Gibbs energy of a minimum. So that can't happen in this situation. And so at high temperatures, when this entropy term dominates, you'll have a Gibbs energy curve like that, and you'll have no phase separation. Whereas at lower temperatures, you'll be down at this situation, across here, and those two compositions are those two compositions, and you'll get a phase separation. And that's how you relate the Gibbs energy curves to the phase diagram you see. At any given temperature, each phase, in this case there's only one, the alpha phase, each phase will have its own Gibbs energy curve, and you can you aim to find a situation where you minimize the energy by forming some combination of phases or of compositions to obtain your phase diagram, and then the compositions you're at you read off as being the phase boundaries in the phase diagram. So let's take an example of that with a situation with two phases. So if you've got two phases, that's the simplest thing we've looked at. The simplest thing we've looked at there is a situation of complete solid solubility. So let's draw out the phase diagram for that situation. So we're moving on from the regular solution model now, and we're thinking of a situation where we had complete solubility in both the solid and the liquid. So we've got our liquid phase L here, and we've got our solid phase S down here. And we'll draw it as being something like that with a two-phase region, liquid plus solid, in between. And at high temperatures, the liquid phase has the lowest energy across all compositions. So its Gibbs energy curve must look, say at this temperature, its Gibbs energy curve must look something a bit like this. This is our Gibbs energy, go from A to B with our fraction of B. And the Gibbs energy curve for the liquid is the lowest one across all possible compositions. So it must do something like that, say. And the solid here, well, it has a curve which is higher across all compositions. So it does something like that. So that's our solid, and that's our liquid. And there we don't have more than one minimum, so we don't have any phase separation of the liquid. I mean, that could happen, but it doesn't in this particular phase diagram. So that's what the Gibbs energy curves will look like, just schematically. When we go on to the solidification point of pure A, then those two must start to overlap. So these two move relative to each other such that just at that particular composition, then the two have the same Gibbs energy. So say if I draw the liquid is here, now the solid must be doing something like this now. That's a solid and liquid going from pure A to pure B for Gibbs energy. So they have the same energy at that particular point. There's only one point where they do, because we're just at that transition for pure A from liquid to solid at a single temperature. When we go down a little bit further into the two-phase region, then something interesting happens, which we'll need to explore a bit further. So when we come down into the two-phase region, then we have a situation where the compositions of the stable, solid, and liquid are there. And we have a Gibbs energy curve that will do something a bit like this. Pure B. And that's our fraction of xb again. And the solid curve will be the lowest energy all the way up to, from here, all the way up to this composition. So that will be the lowest energy all the way up there. And the liquid curve then will be the lowest energy compositions all the way over here. So it will be something like this, say. And then in between those two, we've got a two-phase region. And the two-phase region we can identify in the following sort of way. If we draw the common tangent between the two, where they have the same gradient, that's all the way from here through to here, from those 2 points. And those 2 points are these 2 points. So let's call that some composition solid and some composition liquid. That's these 2 points here. And if we have, so I need to label it, that's my solid and that's my liquid. So the solid is the lowest energy here for all of these compositions over here. I can't form any tie line with the liquid. If I consider this point here, I can't form any tie line that lowers the energy by, so if I take a composition here, say, I can't form a more A-rich with some B-rich liquid that lowers the overall energy. I can't get any lower than that point where I just have solid of that composition. Same is true over here. And in this region here, I can, if I took some solid of that composition or some liquid of that composition, I can decompose it into a B-rich liquid and an A-rich solid and get an overall energy which is down here. So I would have, so I had liquid of this composition here, I could lower its overall energy by forming solid of that composition and liquid of that composition. If it was liquid over here, again, it can come down to an energy there, composed of solid of that composition and liquid of that composition. So these two, these are the phase boundary that we see on the phase diagram. So this is our liquid plus solid region, that's our solid region, and that's our liquid region as we come across the phase diagram at this temperature. And this construction here is very important. This is called the common tangent construction. We actually used it a moment ago when we were looking at the single phase decomposition case. So it's called the common tangent construction. And the way we form it is we form the lowest energy line we can, and that occurs when the gradient of these two is the same, i.e. it's the common tangent. The tangent is the gradient of the line. And if we take the points where we have the same gradient of each of the two, that's the lowest energy line we can form. We're forming a common tangent between them. And where those two touch, that's defining the phase boundaries on the phase diagram here. And the important thing to recognize there is that the minimum in this curve is actually here. It's at zero gradient, whereas actually this thing has a gradient, so it's slightly displaced to the right. Again, the minimum there, and it's slightly displaced to the right there. If it was a line doing that, it would be slightly to the left, but it's not the minimum point, it's the lowest line we can draw. And that's very important. And it's a sort of graphical proof, if you like. I haven't proved this to you using algebra. I've showed it to you on a graph graphically. And I've asserted that the average energy, if you bring the lever rule in, is actually this one on this line. But you can prove that to yourself. But it's a graphical illustration of the idea. And you probably need to be relaxed about that, because we're not going to be able to prove everything algebraically, but we can sketch it to you graphically. So that's what's happening in the solid plus liquid region. There's one other point to look at before we get all the way over to solid here, which would be where the two are unequal there and the solid is lower everywhere else. The other one is if we take a point slightly lower down in temperature, somewhere like there. And here now the solid and the liquid compositions have moved over a bit towards a more B-rich area. So again, we've got our Gibbs energy, kilojoules per mole probably, against our going from pure A to pure B, and that's our increasing fraction of XB. And now we have the same sort of lines, but again, they've moved relative to each other. The solids move down relative to the liquid. So now we'll have a graph that looks something like this, and say, and it'll keep on going. It'll be defined for all compositions, even if it's off the top of the graph. And our liquid will be something like that, say. And then if we draw our common tangent will be somewhere like, if I get my ruler, will be somewhere like there. So you really see on this one that the common tangent isn't at the minimum. So it's here and here. So those are our two compositions. That's our CS now and our CL there. And that's our CS and our CL. And we've got a wider solid region of solid phase. We've got a solid plus liquid. And we've got a liquid phase region. And as we come down in temperature, as these two have moved relative to each other and the liquid's gone further up, what's happened is this liquid plus solid region has translated over to the right. And it's just a sketch, so obviously it's not quite perfectly accurate. But what's happened here is as we've gone down in temperature, the liquid has moved gradually up relative to the solid curve. They've probably changed shape slightly. And we've constructed then the phase diagram at each temperature. And what we then move on to do is then to look on eutectic diagrams, the other type we've seen, and then we'll be done for this segment. So in eutectic diagrams, here's our temperature composition. This is going to be our phase diagram. We've got a liquid phase up here, which has continuous solubility. And we've got a phase here, which we'll call the alpha phase. And we've got a beta phase over here. So the beta phase is B-rich solid. The alpha phase is A-rich solid. And we've got an alpha plus liquid region, a beta plus liquid region, a eutectic point, and an alpha plus beta region. And that's our phase diagram. So what would the Gibbs energy curves look like at different temperatures? Well, the liquid curve will be fairly flat and slowly varying because it has complete solubility. So its energy can't be very high anywhere, really. It can't be very unfavorable anywhere. The alpha phase, well, we only see that at compositions near pure A, and so it will have probably quite a tight, quite a peaky distribution where its energy goes up to being quite large when you get over to high contents of B. And the beta phase will be similar. So it'll look probably something a bit like this. Let's pick a temperature. So we'll pick a temperature, say here. And at that temperature, you see pure alpha phase, alpha plus liquid, and liquid phase. Those are the phases that are involved. So at that temperature, our Gibbs energy diagram is going to look something a bit like this, say. So this is our Gibbs energy. This is going from A to B with the amount of B. And that's going to be in kilojoules per mole, say. And we're at this particular temperature, whatever that is. And we've got an alpha phase. Let's draw the alpha phase in red. And the alpha phase is the lowest energy phase at compositions up to this number here. And then we've got a liquid phase, and that's stable. That's the lowest energy phase across a whole range of compositions, most of them, in fact. So it'll do something, let's say, a bit like this. Well, probably a bit more like this, say. And then we'll have a beta phase. Let's have a third color, a beta phase, and that'll never be the lowest energy phase, so it must be somewhere like that. So that's our beta phase, that's our alpha phase, and that's our liquid phase. And we'll have a common tangent between the liquid and the alpha, so let's draw that in. We've got a common tangent over here, and this number and that number, those two numbers correspond to, that one corresponds to the phase boundary between the alpha and the alpha plus liquid regions. And this number here corresponds to this number here, and that's the phase boundary between the alpha plus liquid and the liquid regions. So that's the situation at that temperature. When we go down a bit further in temperature, then we get to a situation, say somewhere like here, where this is quite complicated now. We've got a situation where alpha is the lowest energy, alpha plus liquid, common tangent will be lowest, liquid, and then beta plus liquid, and finally beta. So we've got lots of regions, 1, 2, 3, 4, 5 regions to be able to draw out on our Gibbs energy curve. So let's do that now. So we'll have Gibbs energy here against content again. So that's G going from A to B. And we'll have our alpha phase now. That's now done something like this. The liquid's probably moved up a bit relative to the alpha. So we'll put it somewhere like over here, and the beta will put, that's probably descended relative to the liquid, because now there's a region of it where it's the lowest energy phase. So that's our beta, that's our alpha, and that's our liquid. So each phase has its own Gibbs energy curve. And now we can draw the common tangents, and if I've drawn this right, the common tangents will work out, and if I haven't, I'll need to redraw it. So there's a common tangent there. There's a common tangent there. Okay, it's not a particularly great diagram, but you get the idea. So this region over here, beta is the lowest energy. Here I've got a common tangent between there and there. It's my liquid plus beta. Here the liquid is actually the lowest energy phase. Here I'm in my alpha plus liquid. I've got a common tangent between there and there. And here's my alpha. And these 1, 2, 3, 4 points correspond to that one, that one, that one, and that one. Obviously, it's a schematic diagram, but we could call that, I don't know, compositions 1, composition 2, composition 3, composition 4, and call that C1, C2, C3, C4, and label it as schematic. And that'd be a perfectly acceptable schematic sketch of how the Gibbs energy varies between them. I've shown that each phase has its own Gibbs energy curve. The alpha one's got to be a slightly tighter curve because it's got a narrower range of solubility than the liquid. The beta is also quite tight. I've got some common tangents between them. I've got some minima, and that's sort of the schematic for what will happen at that temperature. Now, there's another temperature here that's quite interesting. There's this one at the eutectic point. So what's going on there? Well, there, we've got a common tangent in this part of the curve between the alpha and the liquid. And we've also got, at that same point, a common tangent between the liquid and the beta. And what that means is that all three will lie on the same common tangent. So let's sketch that out. So here again, I'll have Gibbs energy. I'll have Gibbs energy against composition, and that's at this eutectic temperature. And I'll have a common tangent between all three of them. So actually I'm going to cheat. I'm going to draw the common tangent in first, and then I'm going to make it work. So I'm going to draw my alpha phase here. I've got a gradient like that. So the minimum's got to be slightly to the right of it. That's my alpha phase. I'll have my beta, which will have a gradient of that there. So again, its minimum will be slightly over there. So that'll be something like what the beta looks like. And then I'll have a liquid that goes somewhere in between. It's going to be smoothly varying. It'll be higher, and it'll do something like that. I mean, it'll actually touch, right? So it'll do something like that. And that'll be my liquid. And that's what it'll look like at the eutectic point. And then finally, we've got our last temperature we can consider, which is down here. And at that last temperature, the liquid will have moved up so far that it's not participating in the equilibrium at all. So at that temperature, then we can draw our last diagram, A through to B, Gibbs energy. And we'll have, this one will be a lot easier to draw. We'll have our alpha phase. We'll have our beta phase, something like that. Actually, let's put it at a slightly different position. Let's put it somewhere like there. That's our beta. That's our alpha. And the liquid will be so high in energy that you can never form a common tangent involving it. So what you'll have then is you'll have a common tangent just between the alpha and beta. So here I've got my alpha region. I've got my alpha plus beta region. That's my beta region. That composition corresponds to that one. That composition corresponds to that one. And just to to draw it here. That's my alpha. That's my alpha plus liquid. It's my liquid plus alpha. And that's my beta at a temperature just at the eutectic point. So that's the set of different diagrams, different sort of schematic Gibbs energy diagrams for how the Gibbs energy will vary at different temperatures through the phase diagram. And what you're seeing is basically the liquid is moving up relative to the alpha and beta phases. So that gradient of the common tangents moved each time until the liquid can't participate anymore and you just have an alpha plus beta phase field. And that's how Gibbs energy relates to phase diagrams and how the thermodynamics relates. Now, at this point in the course, we've done everything we need to now do about thermodynamics and binary phase diagrams in the case where we reach equilibrium. And now we can move on in the course to think about cases where we're not in a complete equilibrium state. And that will take us on to think about solidification and kinetics, the speed at which transformations happen, and to look at the iron-carbon phase diagram in the last couple of lectures of the course.